actually, let me first write for Gz of I omega. So Gz of I omega would be Gz1 of I omega. What does that mean? That means wherever I see S, I put I omega, and Gz2 of I omega, where Gz1 of I omega is K over 1 plus wherever I have S, and I have S here, I put I omega times tau. And Gz2 of I omega you can read that is e to the minus S is replaced by I omega t. Sorry for writing over. Okay? Yeah, computer is in the second. I was just getting ready. Clear, everyone? All right. If I find the real part and the imaginary part, if I find the magnitude and the imaginary part and the phase life of each one of them, any complex number, I can write Gz of I omega as a real part of Gz of I omega plus I times imaginary part of Gz of I omega. But I can also rewrite that as magnitude of Gz of I omega times e to the I argument of Gz of I. We talked about last time how A plus Bi, which is real part plus imaginary part times I, can be rewritten as magnitude of A plus Bi times e to the I argument of A plus Bi. Remember that? Key thing. Everybody remembers it? So, that means for any complex number, like Gz of I omega, which that's the A part, the imaginary is the B part, can be rewritten as magnitude e to the I argument. With me? Let's call that equation 1. I can do the same thing for the two pieces, Gz1 of I omega and Gz2 of I omega. So I can rewrite Gz1 of I omega as magnitude of Gz1 of I omega times e to the I argument of Gz1 of I. And I can rewrite Gz2 of I omega as magnitude of Gz2 of I omega times e to the I argument of Gz2 of I. Let's call this equation 2 an equation. So far so good? Gz of I omega is the product of Gz1 times Gz2. From this follows that using equations 1, 2, and 3, that substituting at the magnitude of Gz of I omega times e to the argument is going to be magnitude of Gz1 of I I omega, e to the I argument of GZ1 of I omega times magnitude of GZ2 of I omega times e to the I argument. I'm trying to squeeze you guys to put in one line. GZ2 of I omega. So far so good? Feeling okay?
Yeah.
So, right hand side, group those two together and group those two together. Remember, e to the a times e to the b is equal to what? E to the a plus b. So, I can rewrite the right hand side as the product of GZ1 of I omega times GZ2 of I omega times e to the I. I is a common factor of a plus b. This is my a, this is my b. I is a common factor, and I'll have argument of GZ1 of I omega plus argument of GZ2 of I omega. With me? Mika.
In order to multiply exponents, don't you have to have them as exponents to each other or something like that?
You have to what?
In order to multiply exponents, don't they have to be exponents of each other? I thought like if you did it, you would be added together.
Yeah, it is additive. Exactly. I multiplied this, and you get the 12 shot. Yeah. This is e to the a. This is e to the b. So e to the a plus b is e to the this plus that. I multiplies both of them. So it's a common factor. So e to the I, from here argument of GZ1, and from here argument of GZ2. Clear? All right, everyone? Now, looking at this equation, this is a positive number, right? Product of two positive numbers. Remember, the magnitude is the distance. And so that's a complex number with this magnitude and this phase line. So looking at the left and the right hand side, from here follows that the magnitude of GZ of I omega is going to be the product of the magnitude of GZ1 of I omega plus GZ2 of I omega. And comparing the arguments, two complex numbers are equal. If two complex numbers are equal, if I have a e to the ib equals c e to the id, the only way this is possible is if a equals c and b equals d. That's possible. So that also means that the argument of GZ of I omega, the argument of the product of the two, is the sum of the argument. Caitlin, what do you use?
The first line, like I get the argument one, like I get the exponents have to be added, but I don't get the magnitudes being added together.
Well,
Shouldn't we multiply together?
oh, yes. What did I write? No wonder you're perplexed.
That's a new
Because
problem.
it should be multiple. second one. Okay.
That makes sense.
No wonder you're perplexed. At least I look at your faces. Messing up. Clear now? Makes sense now? Okay. Very good. All right. So I want you to keep those two equations in mind. I'll call them star 1 and star 2. That's how we're going to find the magnitude of phi omega and the argument of GZ of phi omega. Okay? We're going to find for GZ1 and for GZ2. Okay? With me? So, let's proceed now to find, first of all, what is the magnitude and the argument of GZ1. So GZ1 of S is K over tau S plus 1, which means GZ1 of I omega, where I have S, I put I omega. So that is equal to K over 1 plus I omega tau. Okay, that means wherever you have S, you put I omega. This is the only place I have S, so I stick I omega. And I simply wrote the 1. Okay. How am I going to get the magnitude and the argument of this complex number? If I had it in the form A plus IB, I could get the magnitude, the square root of real part plus imaginary square. So here, let me put GZ1, if I have GZ1 of I omega, real of GZ1 of I omega plus an imaginary of GZ1 of I omega, then the magnitude of GZ1 would be real of GZ1 squared plus imaginary of GZ1 squared, and the argument within GZ1.
Multiply it by 1 minus that.
Absolutely. So, Adam moved correctly. So if I can get it first in the form A plus IB, I can then move forward with what I just discussed. So how can I get it in the form A plus IB? Do exactly what Adam just said. Make the denominator real by multiplying both numerator and denominator by the complex conjugate of the denominator. So that means that complex conjugate means wherever you have I, you replace it with minus I. So I'm rewriting this as K over 1 plus I omega tau times 1 minus I omega tau over 1 minus I omega tau. Okay? And if you multiply something with a complex conjugate, the product of the two is real. So the product of the two denominators, do the algebra, 1 plus I omega tau minus I omega tau minus I squared omega squared tau squared. The algebra. You should know it, but rusty. Okay? These two cancel out. What is minus I squared equal to?
Minus 1.
Plus 1, right?
So I squared is minus 1.
Yes.
Right.
And the numerator is K minus I K omega tau. So I can rewrite this as K over 1 plus omega squared tau squared plus I times minus K omega tau over 1 plus omega squared tau squared. Question okay? Okay.
Let
Let me slow down. If I go too fast, guys, slow me down.
It's my fault. I came a little bit late, so yeah.
I squared is plus 1.
Hmm?
Positive I squared is plus 1.
Minus.
No. I squared is minus 1. I is
But it's minus I squared.
I equals square root of minus 1. I squared is minus 1. Minus I squared is plus 1. The minus I squared became plus 1. Okay. Anybody else? All right. So, this is the real part. This is the imaginary. So now we can immediately write with the magnitude of GZ1 of I omega is going to be the square root of the real part squared plus the imaginary part squared okay? I have a common denominator, so that's square root okay, that's the common denominator, and I have here k squared plus k squared omega squared tau squared. So k squared factors out. We see cancellation, yes. So, okay, word of caution. I'm writing what many textbooks are writing now. Okay? Are we happy with this?
You make it sound like we shouldn't be.
Right.
Why are we not happy with what many books have written? Why about half of the time this is bad? K could be negative. If k is negative, what's square root of k squared? What's square root of a number squared? You should know that. Say, Thomas?
Absolute value.
Absolute value. Right. Should be absolute value, which is k if k is positive, but minus k if k is negative. So watch out for this. There's a tendency for many chemical control textbooks to automatically assume that k is positive. And I'll come back into that again and again. Very bad habit. So that's what the magnitude of G1 of I omega is. Okay, everyone? How about the argument of GZ1? Here I'll use the tan inverse. It's tan inverse of the imaginary part, and the imaginary part is what? Minus k omega tau divided by 1 plus omega squared tau squared. And the real part is what? K over 1 plus omega squared tau squared. Obviously we have a cancellation. This will cancel. And also the k is